Welcome to lecture 24 of Introduction to Quantum Field Theory. In this lecture, I will continue the discussion of symmetry in conserved quantities that we started in the last lecture. To get started, recall that in lecture 22, we found the action S for a complex scalar field phi. And we found that in addition to Lorentz invariance, this classical action was invariant under an additional symmetry, namely a symmetry under the transformation phi going to phi prime is e to the I alpha times phi, where alpha was an arbitrary constant. In the last lecture, we discussed the Noether theorem, which is the consequence of a conserved quantity arising from a classical symmetry, such the symmetry given in this equation here. In particular, for the complex scalar field, we found that there is a conserved quantity that is written as a classical conservation law d mu j mu is 0 for the Noether current j mu that in case of the complex scalar field is given as twice the imaginary part of phi star d mu phi. Now, the discussion in the last lecture was purely on the classical level. So in this lecture, I want to ask what happens if we want to derive a quantum version of this conservation law. To get started, I have to tell you a little bit about how to set up quantum field theory in Minkowski spacetime. For most of the lectures, we have set up quantum field theory through the partition function z, which was a path integral over the exponential of minus the Euclidean action. The idea being that the Euclidean action is the action that we get in imaginary time, and the advantage of this formalism is that if we can formulate the field theory in Euclidean spacetime, then these integrals here are all well defined, they converge, and we can actually make sense of the object such as the partition function. That's just saying that in imaginary time, if we have a Euclidean field theory, the integrals converge and we have a well-defined object, even if we discretize, for instance, the path integral. However, we can formally obtain results in Minkowski spacetime by analytically continuing from imaginary time to real time. Some of this has already been discussed in lecture 16, when we were discussing the analytic continuation of the propagator to Minkowski spacetime. It is possible to formulate all of the things that I'm saying first in Euclidean spacetime and then at the end of the day analytically continuing to Minkowski spacetime. However, I find it more straightforward to just formally write down analytic continuation of this path integral and deriving this result in the way that this can be justified through a sort of more careful analytic continuation. So long story short, what I want to do is I want to write down the partition function z as a path integral over e to the is, where s here is now the Minkowski action, meaning the action that we have written down for the complex scalar field in lecture 23. So basically, the Euclidean action was just formally continued where we took time, imaginary time, and converted it back to real time, and that explains the difference from the minus s to the is here. For a complex scalar field where we have two independent components, phi and its complex conjugate phi star, we then find that the partition function is given as the path integral over d phi star of e to the is of phi and phi star. We know that the classical Minkowski action S is invariant under the symmetry phi going to t e to the I alpha times phi. That's the symmetry spelled out in equation 24.1. And what we want to do now is we want to investigate what happens if the symmetry is a symmetry of the full quantum field theory, not some classical approximation, but it really is a symmetry of, for instance, this partition function. If it is a symmetry of the partition function, it does not matter whether we write down the path integral over the original fields phi or over the transformed fields phi prime and phi prime star, because it should be the same. if the theory is actually has really an invariance under this particular symmetry. If the symmetry is a symmetry of the action, we find that delta S, meaning the variation of the action with respect to the transformation, or for small variations, the difference between S of phi prime and phi prime star and the unprimed fields has to be 0. In lecture 23, we found an explicit expression for delta S by varying the action of the complex scalar field. And we found that for any small change of phi, delta S was given as this expression here. Now, what we want to do now is that we want to generalize the symmetry for which we know the action is invariant to a symmetry where alpha here, the parameter, the exponent, is now position dependent. This is a change from the original symmetry because the classical action is not invariant under this full symmetry here. However, we found that because delta S for any small change, delta phi, is given as this expression given in 24.8, this integral is an integral over total derivative. So that meaning for any small change, delta phi, this action will be invariant. The difference being that the original symmetry would also hold beyond linear order. But to linear order, we have an invariance of the action for any small change, delta phi. So for small parameter alpha, we have delta phi is just E alpha x phi of x. That's just the variation of the exponential. And plugging this result into the explicit formula for the variation of the action, we get delta S is the integral of x d mu of this expression here. We recognize the expression in the bracket here to be nothing else but the classical current J mu. So we can replace the object in brackets just by J mu. So we find that delta S is equal to the integral over d mu alpha of x J mu of x. We can use the chain rule to split this into two parts, where the first part is alpha d mu phi, alpha d mu j, and the other one is j mu d mu alpha. And we can then use the fact that the classical current J mu is conserved to get rid of this first term. So using d mu J mu phi 0, which we can show explicitly, we find that delta S is just given as an integral over J mu d mu alpha. As a consequence, we can write e to the is of the primed fields using small variations to be equal to e to the is of the unprimed fields, the original fields, plus a small correction term, delta S. And since delta S is small, we can expand the exponential, and we find that this is equal to e to the is times 1 plus I integral over this expression here. In addition to the action, for the path integral, we also have to look at what happens to the measure. Plugging in the explicit form of the symmetry, we find that the Jacobian, if you want so, of the field phi prime is just given as e to the I alpha of x. And the Jacobian of the transformation of the complex conjugate is given as e to the minus I alpha x. What this means is that the measure d phi prime star is invariant under this combination because the terms, the Jacobian of the phi and the phi star fields just cancel. So we find that the measure of the path integral is invariant under this local change that we've written down in equation 24.9. Again, recalling that delta S vanishes for any small delta phi because it's an integral over total derivative, we find that the action has to be invariant under this generalized transformation where alpha is a local parameter to linear order in alpha. We can't say at this point anything about higher orders, but to linear order, this is a symmetry. And we can just exploit this symmetry. So we find that the integral, the original path integral that we wrote down, d phi star of e to the is, is equal to the integral of the transformed fields using this transformation to linear order in the parameter alpha. We have discussed that the measure is invariant under these transformations. We have discussed how the transformed action looks like to linear order in alpha. And we can just essentially bring this term here to the right-hand side and just look at the variation of this action or this path inequality to linear order in alpha. What we find is that if we bring this term to the right-hand side, we have 0 on the left-hand side, and on the right-hand side, we only have terms linear and alpha that remain. And if I just recall that we have written down the variation of the action of the prime fields as 1 plus I alpha, this variation here, we find that the invariance of the quantum P theory with respect to this transformation to linear order then gives us a result that says 0 is equal to integral over x, derivative of alpha, times the path integral of the current J mu. Now, we can recognize this path integral here to be nothing else but the expectation value of the classical current J mu, or the classical current operator J mu, in the full quantum field theory, because we're not doing perturbation theory. So S here is the full action, including all interactions. If we do integration by parts, we find that this is equal to integral over x alpha d mu, the expectation value of the current. And alpha x here is small, but it's still arbitrary. So what that means is that we can choose alpha to be, for instance, expanded in a complete basis of functions. So for instance, Fourier series with arbitrary coefficients. And what that means is that since we can expand it with an arbitrary basis with arbitrary coefficients, any such choice must have vanishing integral. And the only possibility for that is that the integrand itself vanishes. So at the end of the day, we find that 0 has to be equal to the derivative of the expectation value of the current in the full quantum field theory. So we find that in quantum field theory, the expectation value of the current operator is the thing that's conserved. This generalizes the classical conservation law that we started out originally. And this concludes the present lecture.